Welcome back. We are into the 42nd lecture. We proposed to have about 56 lectures, so we are into 3/4 of our course. And today we are going to revise the notion of eigenvalues and eigenvectors for n by n matrices. This is the stuff that you would have done in your linear algebra course, so we would go rather fast in this, and we would look at some ways to compute eigenvalues and eigenvectors in the coming lectures. So let me start sharing the lecture slides. Okay, yeah, so I hope you can see the lectures now. So yeah, so what we have been doing until now to solve systems like ax plus equal to b, ax equal to b, they are called the direct methods. To give you an analogy, suppose you are given a quadratic equation, say ax square plus bx plus c equal to 0. This is the quadratic equation. To solve this, we have a formula which is given by minus b plus minus under root b square minus 4ac, and then the whole thing divided by 2a. That's the formula that we know. So applying that formula directly will give you the solutions in some way, and though that will be the direct method, but there are these other Newton-Raphson method, or in general some iterative methods that we have used in some previous lectures. So we would like to see analogs of those kind of iterative techniques again to solve our ax equal to b. This is what we would want to do in this lecture. So how did we apply the iterative techniques for equations in one variable? What we did was that there was an initial approximation, or maybe a few approximations to begin with. They were found, and new approximations were then determined based on how well the previous approximations satisfied the equation. The objective basically is to minimize the difference between the approximations and the exact solution. So that's the thing that we would want to do. But to discuss these iterative methods, when you are looking at Rn, we have to think about how to measure the distance between two vectors. What we had in R was that there was this absolute value which would compute how far the exact solution is from the approximation. Now in Rn, or in general for matrices, you will have some matrix. Even a vector in Rn is a column matrix. So if you are given a matrix and then there is another matrix, we want to know whether there is a way to compute the distance between these two matrices. So that is the thing that we want to do, and we begin with Rn. Our underlying set is Rn, which is the vector space of all column vectors of size n cross 1. We are talking about vector space because we will have to subtract and multiply by scalars and so on. So good to remind you that it's a vector space and all these operations are possible. There are two main types of distances that we are going to define on pairs of vectors in Rn. Suppose you start with these two vectors x and y in Rn, and suppose x is given by x1, x2, xn, y is also given by y1, y2, yn. There is a transpose which is missing here. Okay, so there are two distances that we are going to define. The first one is called the L2 distance, which is defined by taking the differences of the corresponding components. So from x1 you subtract y1 and take the square. From xn you subtract yn and take the square. So you have this x1 minus y1 square plus x2 minus y2 square plus dot 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 xn minus yn whole square. You take the sum and then take the square root of this whole sum. This is defined to be the distance, the L2 distance. And then there is one more distance, which is L infinity distance, which is simply the maximum of this mod xi minus yi. So you take x1 minus y1 and all the way up to xn minus yn, put modulus sign for all of them and take the maximum. That is the distance in L infinity distance. I will not go into the abstract definition of what one means by a distance. There is a definition of a distance function. You know, distance is taken, which is distance of two vectors is computed. So distance is really a function from Rn cross Rn to real numbers. And then it should take positive values and blah, blah, blah. So there are some conditions which we will use freely, but we will not go into the definition of distance. I think it's better to work with these explicit examples of the distances, which are the most useful distances for us. Okay. Let's do an example. So suppose we look at this particular system of linear equations, and you will perhaps notice that it has exact solution x equal to 1, 1, 1 transpose. So if you put x1 equal to 1, x2 equal to 1 and x3 equal to 1, then this is the solution for the corresponding system. But suppose we apply the Gaussian elimination method using 5-digit rounding arithmetic, and suppose whenever we need partial pivoting we apply that, then we get this particular approximate solution, which is 1.2001, 0.99991 and 0.92538. Now what we want to do is to compute the distance of this approximate solution from the original solution, and we will compute it in both the L2 and L infinity distances. We want to see how far x tilde is from x using both these distances. So let's remember what is the difference of the corresponding values. This is 2.001. Here you will get 0.00009 and this will be 0.07462. Okay, so these are the distances of the corresponding coordinates. Let's apply the definition. So for x1, x minus x tilde, L2 distance will be, we take the differences and take the squares. So 0.2001 whole square, 0.00009 whole square, and 0.07462 whole square. And after taking the squares, we summing, and after summing of these squares, we take the square root, and that turns out to be 0.21356. The L infinity distance is, you simply have to take the maximum of the moduli, so we do not put a sign, and then it is easy to see that this is 0.2001. Now if you were looking at these solutions component wise, then you would notice that the second and third, in fact second component is a very good approximation. You had the correct solution for first 4 digits, and even in the third component you had it to be correct for the first decimal digit. Okay, but your first component is a very poor approximation and that has dominated. So that error dominated the computations of both these distances, and that is very natural, because if even in one component, if the distance is not nearby, if the error is large, then you would expect that the vectors are not close to each other. We expect that two vectors are close to each other if for all the components, the corresponding components are close to each other. That is expected. Okay. So the notion of distance that we have now defined, that can be used to define convergence in Rn. We will say that a sequence of vectors, say Vn or Xn, converges to a vector X if the distance between xn and x can be made as small as you want. You know, we have that epsilon and capital N that can be brought in with your usual modulus being replaced by either the L2 norm or the L infinity norm. And I will give you this basic inequality to tell you that whenever something goes to 0 in one norm, it will go to 0 in the other norm also. So if your L2 norm is going to 0, L infinity norm has to go to 0, because the L infinity norm is always less than or equal to the L2 norm. 0.2 is 001 is less than 0.21356. Moreover, if your L infinite or norm is going to 0, multiplying to that by root n, which root n is fixed because root n is for the Rn. So root n times that L infinity distance will also go to 0, and therefore the L2 distance has to go to 0. So the convergence is going to be independent of L2 or L infinity. Whether you define the convergence with respect to the L2 distance or L infinity distance, it doesn't matter. If your sequence is convergent to a point with respect to one distance, it will be convergent to the same point with respect to the other distance also. So don't worry about that. All right, and now we go towards matrices and defining norms on matrices. We started with vectors. Now we are going to n by n matrices, because we want to talk about distances between matrices also. Okay, so the norm is actually the generalization of the absolute value, but before going to matrices, we have norms on Rn also, and that is simply the distance from 0. So L2 norm of a vector x is simply summation of mod xi square, the whole thing raised to 1 by 2. And the L infinity norm is the maximum of mod xi. So these are the analogs of absolute value on Rn. And now if you want to think about matrices, that is very easy. Once again, we have two norms on matrices. The L2 norm is given to be in the following way. So let me just give both of these and explain these to you. What happens is that capital A is a function from Rn to Rn. When you start with an x in Rn, the Ax is also in Rn. Okay. So what we do is as follows. You take all vectors x whose L2 norm is 1. Okay. Apply A to all these vectors. Then take the L2 norm of the resulting vectors. And among all these real values, you take the maximum value. That is defined to be the L2 norm of the matrix A. Similarly, the L infinity norm is defined. You take all vectors in Rn whose L infinity norm is 1. Apply the matrix A to them, then you get various vectors in Rn. You take their L infinity norms, so you get various real numbers, and now take the maximum. You define that to be the L infinity norm of your capital A. So there are these two norms. We need to worry about computations of these norms. There are very nice formulae to compute, because to look at all those vectors whose L infinity norm is 1, that can be a tedious job. There are uncountably many vectors of L infinity norm being equal to 1, and then you will apply the matrix A. You try doing it for a 2 by 2 matrix, and you will see that although it can be done with some effort, it is desirable to have some nice formulae. And so we have the formulae to start with for the L infinity norm. The L infinity norm on matrices is basically maximum over the rows of the entries in a row summed under modulus sign. That's all that we need to do. So what you do is that you fix a row of your matrix, put modulus to all the entries in the row, and take the sum of now these non-negative numbers. Once you have done it for each row, you take the maximum over all the rows. That is the L infinity norm of your matrix A. For instance, suppose we start with a matrix given by this way: 1, 2, minus 1, 0, 3, minus 1, and 5, minus 1, 1. And we want to compute the L infinity norm. So we start with the first row: 1, 2, and the modulus will give you this to be 1. So 1 plus 2 plus 1 is 4. The second will be 0 plus 3 plus 1, which is 4. And the third is 5 plus 1 plus 1, that is 7. So the maximum among 4, 4 and 7 is 7. So the L infinity norm of our matrix is 7. Very easy computation. Now we need to worry about computations of the L2 norm. But before we go towards that, we have to just revise quickly the notion of eigenvalues and eigenvectors. And this is related to the L2 norm. That's why we are doing it. But of course, we will also use eigenvalues and eigenvectors later in the course. So an n by n matrix A acts as a function from Rn to Rn. and the eigenvectors are vectors that are sent to their multiples by the matrix A. But is 0 an eigenvector? Because 0 will be sent to 0 by every A. And therefore, if we just take this as the definition, then 0 will try to come force its way in the set of eigenvectors. But 0 becoming an eigenvector for all matrices is first of all little bit weird, and it's of no use at all. So we don't take 0 as the eigenvector. What we take is that a non-zero vector V in Rn is called an eigenvector if you have that AV is lambda times V for a real number lambda. This is called an eigenvector. Where is an what is an eigenvalue? A real number lambda is called an eigenvalue if there is a non-zero V in Rn with AV equal to lambda V. So the vector has to be non-zero, because otherwise what happens is that every value will be an eigenvalue. If your V is allowed to be 0, you will see that A into 0 is lambda into 0 for every lambda. And so you will have too many eigenvalues to deal with, and that's also not a correct thing to have. We don't want to have infinite. And in fact, every real number will be an eigenvalue, and then there is no sense. If your everything satisfies the definition, there is no sense in having the definition. So how do you compute eigenvalues? How do you compute eigenvectors? So for eigenvector, you have to find the lambda, which is an eigenvalue. And for an eigenvalue, again, you have to find a vector, which acts as the corresponding eigenvector. So there is another way to compute eigenvalue. The definition of eigenvalue and eigenvector is the one that we have given. Now the method that we are going to compute, that's a method to compute eigenvalues. That's not the definition of eigenvalues. Okay, so whenever lambda is an eigenvalue, we see that there is a non-zero vector V with the property that AV equal to lambda times V. So if you look at the matrix A minus lambda times I, it sends a non-zero vector V to 0, and therefore it cannot be an invertible matrix. An invertible matrix cannot have, say, some non-zero vector going to 0, right? And therefore the determinant of A minus lambda I as a polynomial, it has to be 0. Now this is what is called a characteristic polynomial of A. The characteristic polynomial of the matrix A is determinant A minus lambda I. So the eigenvalues are roots of these characteristic polynomial. This is a way to compute eigenvalues. After computing these roots of the characteristic polynomial, you have to come back and find an eigenvector. If you get an eigenvector, then lambda becomes an eigenvalue. Every root of the characteristic polynomial is not an eigenvalue, because even though you are working over real numbers, you may have, so determinant A minus lambda I will be a polynomial with real entries that may have complex roots. And clearly a complex root will not satisfy this equality AV equal to lambda V, where V is a real vector. Therefore, a complex root which is not a real root, Therefore, all roots of the characteristic polynomial are not eigenvalues. For eigenvalues, you have to get the corresponding eigenvector. So let's take an example. We want to find eigenvalues and eigenvectors for this matrix 2, 0, 0, 1, 1, 2 and 1, minus 1, 4. We compute the characteristic polynomial, which turns out to be this cubic polynomial. The characteristic polynomial will always be in the same degree as the size of the matrix. This has roots lambda minus 3 and lambda minus 2 whole square. And so these are the two possible eigenvalues, 2 and 3. We now need to find the eigenvectors. To compute corresponding eigenvectors, we have to look for vectors V with A minus lambda I into V equal to 0. This is what we have to compute. So although we have to still compute eigenvectors, I have already declared that these are the eigenvalues. That's the reason for that is that these are real numbers. So when you have real numbers which are zeros of the characteristic polynomial, then there are always eigenvectors. We will not go into the details of that, but let's find now the eigenvectors for 3 and 2. So suppose if I take lambda equal to 3, a minus 3 identity acting on v equal to 0 will give you this kind of a system. When you write it down, you will get that v1 is 0. Already the first column says that minus 1 into v1 is 0. So v1 is 0. And once you have v1 equal to 0, you ignore the first column. You get minus 2 v2 plus 2 v3, which is 0. And also minus v2 plus v3 equal to 0. So v2 is v3. So for instance, 0, 1, 1, that's an eigenvector. But any non-zero multiple of that will also be an eigenvector. So given an eigenvector, there is a unique eigenvalue. But given an eigenvalue, there is no unique eigenvector. The eigenvectors form a one-dimensional space except the zero element, or maybe even higher dimensional space. For lambda equal to 2, we again need to compute a minus 2 identity v equal to 0. And so a similar analysis will have to be done. And what we get in the end is that we get this solution v1 minus v2 plus 2 v3 equal to 0. And if you declare what your v1 is, then you get the solution that 2v3 equal to v1, depending on what your, if you declare v1 to be 0, for instance, then you have 2v3 equal to v2, and so that gives you a one-dimensional vector space. Or if you declare v2 to be 0, then you get 2v3 equal to minus v1. So you have, by putting v1 equal to 0, we get 2v2, v3, which is 2 times 1, is v2, which is 2. Or if you put v2 equal to 0, we get 2v3, which is 2, is negative of v1. So it is minus 2. So these are the two possible eigenvectors, and you can take a linear combination of these with non-zero scalars. By non-zero, I mean at least one of them has to be non-zero, and then you get an eigenvector for lambda equal to 2. This is the calculation how one computes eigenvalues and eigenvectors. Now we go to the notion of spectral radius, which will help you computing these L2 norm of a matrix. So what we do, of course, is that even though your A may have real entries, some roots of the characteristic polynomial may be non-real complex numbers. This is again to emphasize, because we are going to define the spectral radius by maximum of mod lambda, where that lambda will vary over all roots of the characteristic polynomial. So these are not just the eigenvalues, but all the roots of the characteristic polynomial. Excuse me. Okay, so once we have, so spectral radius is what? You compute all roots of the characteristic polynomial, put the modulus on them, and take the maximum value. That is the spectral radius. Now, if you have an n by n matrix, the L2 norm is related to the spectral radius in the following way, that L2 norm is simply compute A transpose A. Okay, so A transpose A is a matrix. You take the spectral radius of that matrix, so you will need to compute the eigenvalues of that matrix, put modulus of them. Eigenvalues are roots of characteristic polynomial, but notice that the matrix A transpose A is a symmetric matrix. So we are all right. We compute eigenvalues, take the modulus, and take the maximum entry. That gives us a real number, which will be positive because you are taking maximum of positive entries, non-negative entries. Then you take the square root of that. This is the L2 norm of the matrix A. Moreover, we have that the spectral radius is always less than or equal to the L2 norm. So the spectral radius of your matrix is always less than or equal to L2 norm, and it is also always less than or equal to the L infinity norm. So these are the properties which relate spectral radius with the L2 norm and the L infinity norm. Let's do one computation of an L2 norm. So take the matrix A, which is 1, 1, 0, 1, 2, 1, minus 1, 1, 2. It's not a symmetric matrix, but we compute A transpose A. or A transpose. What happens is that A transpose and A transpose A are related to each other, and their eigenvalues will be the same. So this is the matrix 3, 2, minus 1, 2, 6, 4, minus 1, 4, 5. That has to be a symmetric matrix. Compute the eigenvalues. They turn out to be 0 and 7 plus minus root 7. The maximum, if you take the moduli, all these are non-negative numbers. So you have 0, 7 minus root 7 and 7 plus root 7. So clearly the maximum is 7 plus root 7, and therefore the spectral radius of A transpose A is equal to 7 plus root 7 under the square root. It will give you the L2 norm, which is 3.10576. So this is how the L2 norm is computed, and let me just introduce one more concept before we complete this lecture. This is the concept of a convergent matrix. So in studying iterative matrix techniques, what we will need to do is to know when powers of a matrix become small. That's something of our interest. And so what it means is that when you take a matrix, you keep taking various powers of the matrix. So you take a square, a cube, a to the 4, a to the 5, and so on. And when you keep taking the powers, the entries of the powers should go to 0. That is what we want. Such types of matrices are called convergent matrices. So the definition is, you start with a convergent matrix. So we call a matrix A to be convergent if for every entry, so every ij, limit of a power k ij as k goes to infinity is 0. So you keep taking, for instance, if you were to take identity matrix, you take all powers of identity matrix, you are just going to get identity matrix, and then the diagonal entries will remain 1. They will not go to 0. So identity matrix is not a convergent matrix. On the other hand, this matrix 1 by 2, 0, 1 by 4, 1 by 4, 2. If you compute powers of this matrix, they are given in the following way. It's a lower triangular matrix. So you get 1 by 2 power k as the diagonal entries of a power k, and this turns out to be k upon 2 power k plus 1. You will be taking the powers. This can be proved by induction. Now if k goes to infinity, clearly 1 by 2 power k goes to infinity. So the diagonal entries, 1 by 2 power k goes to 0. So the diagonal entries go to 0. Above the diagonal, you have 0 anyway. And now this lower diagonal entry, lower triangular entry, we notice that 2 power k plus 1 goes to infinity much faster than k. And therefore, k upon 2 power k plus 1 will go to 0. And therefore, this is a convergent matrix. And convergence matrices have some very, very important and very interesting properties, which is the last slide of this lecture. The following statements are equivalent. Your A is a convergent matrix if and only if the L2 norm of A power n goes to 0, if and only if the L infinity norm of A power n goes to 0, if and only if the spectral radius is less than 1. This is something which is very important. And finally, the nth power applied to any vector v, and then you take the limit as n going to infinity, that goes to 0. So with this, we finish this 42nd lecture. We are going to continue it from our next lecture on the theme of eigenvalues and eigenvectors, and we will see more of these iterative techniques to solve the Ax equal to b part, and also to find eigenvalues and eigenvectors. So stay on with me, and see you in the next lecture. Thank you.